morning. Welcome to your first challenge. It's called Basketball Drill. This is Mr. Afflerbach. So let's see what we're going to do today. So the challenge itself is going to be you're going to get your robot and you're going to start in the box. You are going to drive 1 meter, then stop and then go back and do 2 meters, stop and then go back. 3 meters, stop and go back. And 4 meters, stop and go back. For those who haven't played basketball, that's called the basketball drills. And usually you do it for the foul line and then the half court line and the other foul line and then the whole court. And you got to keep it going for the whole time. So that's called the basketball drill. So let's see what we're going to call the pseudocode. I don't know if I've talked about this yet, but the pseudocode is going to be your plan that you're going to operate for your whole process. So let's look at what the pseudocode is. And the idea here is you write this in English so you can understand what you're doing. And it's really like the plan for your program. So we're going to take this into a bunch of different parts. So let's look at this. So the first two are going to be move forward, move backward. So that's the first two steps or first two tasks. The next two are going to move forward for 2 meters, move backward for 2 meters. Then we're going to, guess what? We're going to go 3 meters and then move backward 3 meters. And then the last one is, or the last two are going to be move forward 4 meters and move backward 4 meters. So that is going to be what we're going to call our pseudocode. So I have these numbered because this is the order that we're going to do the process. So we're going to move forward first, we're going to move backward, and then we're going to do 2 meters, 3 meters, and then 4 meters. So we should end up somewhere around the box when we're done. All right, so we're going to talk about something new. Actually, the new global variable this time is something that we've already talked about. So we're going to put a comment in there, global variables. And we've talked about this in our last episode of Talbot TV, where we have an integer and norm p is the name and is going to give a value of 63. So we're declaring it. It's an integer. It's going to have a name. It's going to say be norm p, and we're going to give it a value of 63. And then, as always, we have a semicolon. And we're going to say what we're going to actually call this. So this is actually going to be called norm p, or normal power. So if someone else reads this with our comment, we'll be able to figure this out. So here's a couple other new concepts, So we're going to start off with a control structure. Now, this is something that is going to be, we're going to pick some control structures up in a little bit, but right now we're just going to have task main. And task main is really where everything happens within our program. So this is where all of our, a lot of times I call this the main part of the program because this is where all the action happens. And one of the things with control structures, we're going to have an open curly bracket to open in this case, task main. And we're going to have the code that we want to use. And then we're going to have a closed curly bracket. So we'll learn some of the next couple of things are going to be simple commands, and they're always going to end in a semicolon. Well, control structures always have curly brackets. And in the beginning, we're just going to have one curly bracket after task main in the beginning to start it, and we'll have one at the end. But then as we get more control structures, we're going to have more curly brackets to keep track of. So that's going to make it a little more challenging as we go, but we'll figure that out as we go. Next thing, we want to get a simple command. So simple commands are going to have semicolons at the end of their commands. So the first thing we want to do is we want to set the motor power. So how do we do that? So the first thing we do is type in the word motor, and notice that it's lowercase. So this is actually the command itself. Then we have to tell it which motor we want to talk to. So in this case, we're going to talk to the right motor. Now, everything that we've talked to that has to go through the cortex is going to have square brackets. So notice that right motor has square brackets on it. So we have motor, square bracket, right motor, close square bracket, and then just like a variable, we have to give it a value. So in this case, we're going to say equals, and we're going to say norm p. So norm p, and then since this is a simple command, we're going to get a semicolon at the end. Now, when we do this, if I were to do just this, we would end up, our robot would just go in circles because we're only moving one motor. But we want to actually move both motors, so we're going to do the same exact thing, but we're going to talk to the left motor this time, and we're going to give it the same value of norm p. So that is the set of commands that we should put into our motor section of our notes, so that when we look at this, we say, well, how do I get my motor to start again? I have to use motor, square bracket, tell me what motor it is, square bracket, and is equal to norm p. All right, or whatever value we want to set it at. All right, the next simple command that we're going to talk about is the pause or wait. So this is wait 1 msec. Now what this is saying is we're going to wait 1, and then m stands for milli, and then seconds. So this is called the wait 1 msec command, and we're not talking to the cortex through this one, so all we're going to need is some parentheses. So we're going to open parentheses, and then we're going to put a value in there, and we'll figure out what this value comes in a little bit later. And then we're going to close our parentheses, and then we're going to put a semicolon. So this is saying that we're going to wait or pause 1.85 seconds. Now, what is a millisecond? A millisecond is 1/1000th. So it would be basically taking 1850 divided by 1000, and that's going to be 1.85 seconds. So if I wanted it to be 2 seconds, it would be 2000, or 5 seconds would be 5000. And again, we'll see a little bit later where the 1850 comes from. Right, the next thing we want to do is we're going to calculate where does that 1850 come from. So let's look at a little bit of the science here. So we've got a wheel, and these are the same wheels that we have on the front of our robot. They're 4 inches in diameter. And if I look at this wheel, I put a spot there, I put an arrow on the wheel, and I put a spot, and I rotate this wheel. Okay, one complete revolution is going to give me a certain distance. And this is the distance traveled in one revolution. Now, this one revolution just happens to be equal to the circumference of the wheel. So that's something that's interesting. So when the wheel rotates one time, it rotates the distance of the circumference of the wheel. So we know circumference from, I would say, probably geometry. And so circumference is equal to pi d, where pi is pi, and d is the diameter of the wheel. So there's the diameter. In this case, it's 4 inches, and we convert this to meters. And that's going to be 10.3 centimeters, or 0.103 meters. And then we plug the numbers in, and we get a circumference of 0.324 meters. Now, since we're running in meters, and the first challenge, or the first part of this challenge is to go 1 meter, it doesn't make sense to keep it in inches, and then we have to convert it later. So we converted it early, and then just made everything into meters. So we'll talk in meters. So we have 0.324 meters. That's going to be our circumference. So we're going to keep that one in the back of our mind. Now, the next thing we have to realize is how fast is the wheel rotating? So that's also going to be telling us how fast we're going. I mean, how much time it's going to take to get there. So we have something called angular velocity. Now, this is a term we actually pick up in physics, so I'm not going to go too deep into it. Its symbol is actually a lowercase omega in the Greek alphabet, and it's actually measured, or oftentimes measured, in revolutions per minute. And how many times does it revolve in 1 minute, or how many revolutions per minute? And we're actually going to convert that to revolutions per second a little bit later. So how fast is the wheel rotating? Well, we need to go and look at a curve. Now, we developed this curve in Robotics 2, and it was a little bit of a surprise to me. I would have thought that at 50 power would be 5 times it was at 10, and 60 would be 6 times what it was at 10. Well, it turns out it's not very linear at all. It actually arcs a little bit and then kind of flattens out towards the end. So we're actually going to have to use this chart to figure out how many, if I have 63 power, and we'll talk where 63 comes in a little bit, and then how much my revolutions per minute are going to be. So I can actually put a line in there. Oops, I lost my line. There we go. And we then have a power of 63, and we have a wheel speed of approximately 100 revolutions per minute. Now, we really didn't talk about where 63 comes from. 63 comes from, it's really basically half of 127. Now, 127 is the maximum speed or maximum power I can put into a robot. And what happens is it ends up getting something called momentum. And if I want to stop, like I want to do in this case, I actually, at 1 meter, I want it to stop. I don't want it to stop at 1.2 meters or 1.1 meters. I want it to stop exactly at 1 meter. And it's very hard to stop something if it's going too fast. So what we decided, or I decided, is to pick a half power so that it doesn't have so much momentum at the end. So when I want it to stop, it stops pretty regularly and it's not as hard to stop. For those who have had physics, remember momentum is going to be a function of the mass of the object times the velocity. So the faster I go, the more momentum it's going to have, since our robots are all going to have the same mass. So we're going to say that my angular velocity is equal to 100 revolutions per minute. And we're actually going to convert that into revolutions per second, so that we can, and it's 1.67 revolutions per second, so that we can make our calculations a little bit better. All right, so now here we go. We're going to calculate all of this. So this is all the stuff that we know. All right, so I know my circumference, I know my omega, I know my distance to travel, which is going to be 1 meter. And there we go, put the meter in. Now here's my equation. Okay, time is going to be the distance that I travel, which is 1 meter, divided by c, the circumference, times omega. So when I plug all that stuff in, I actually get a time of 1.848 seconds. And if I convert that into times 1,000, if I convert that into milliseconds, that's going to be 1848 milliseconds. Or if I just want to round that up, it comes out to 1850. So that's where my 1850 comes from. All right, so let's code. All right, so here's our code. This is our brand new file. We just opened it up. So the couple things that since this is our first time actual coding, we're going to have to set some things up. So the first thing we're going to do is to go to File. It's in the top left corner. I don't show it on the screen here, but it's in the top left corner. You pull down, you hit the word New, and then you want to click New File. And then once you do that, you're going to get a file that's going to look like this. It's actually going to have a task main in there, but we're not there yet. And then once you do this, you're going to hit File and then Save As, and we're going to call this Challenge 1. Surprise, surprise. And then what I would do is I would make a folder inside on my desktop just called Robotics 1. And then every time we do a challenge, you just put all the files into Robotics 1. Another thing that we're going to find out is it's really a good idea. Once we set it up the first time, all we do, when I do start challenge 2, I'm actually just going to open up challenge 1 file and then edit challenge 1. We're going to edit and then save as challenge 2, and then we're going to save as challenge 3, and then 4, and then 5, and all the way up. So I don't have to go through all these steps every time. So once we do that, we've got task main that's already going to be inserted. Now I've got to do something else. We're going to go into motors and sensor setup. It's up here in the blue box. You can see it. It's right there. And you're going to go into the actual setup for the robot, and it's going to have you select a type. And if you select a type, it's going to, about halfway down the screen, it says RVW Clawbot. Now, if you don't have a Clawbot on your list, that means that we have to go back, and we're probably into the IQ, and we have to go and set up our robot to look at Cortex, because Cortex is going to give you the Clawbot. So once you select your robot, you're then going to hit OK, and then what's going to happen is you're going to get something called a pragma statement. Now, a pragma statement is going to show up at the very first of the program, and it's really important that this is at the very beginning, because this is kind of like a variable, and it says, you know what? This is telling everybody what I'm running. It's going to say, hey, everybody, I've got a Clawbot, and it's got motor 1 is going to be my left motor, motor 6 is going to be my arm motor. I don't know. I think that's the claw motor. 7 is going to be my arm motor. Then 10 is going to be my right motor. And then all my sensors are already set up, so you don't have to worry about that. So it tells everybody what each thing is. So we don't have to worry about identifying which motor is which because we've already have them already plugged in. So it's already set up that way for us. So a pragma statement is going to be in the very beginning. Now, one thing important about a pragma statement is that you do not want to edit it manually. If you do have to edit it at all, which you really shouldn't have to, you should edit it through the motors and sensors setup. You should not enter it or edit it manually. All right, so now we've got this, and I've got challenge 1, and I'm going to now insert my global variables. Now, remember when we talked about global variables, they go outside of task main, and they're going to go between the pragma statement and task main. So we're going to move task main down a little bit. We're going to put a comment in that's going to say global variables. Now, notice that this is plural right now. We're only going to put 1 in for challenge 1, but challenge 2, we add 2 more. So we're actually going to have a couple of variables coming up. So, and just as we've said our int norm p is equal to 63. Again, this is declaring that norm p is an integer, and it has a value of 63. All right, now the next thing we've got to do is we've got our variable in, and we've got our pragma statement. We've got task main ready to go. It's got a big space in there waiting for things to go in there. And we pick up our first line from our pseudocode. So if I look at my pseudocode, it says move forward 1 meter. So we add that as a comment. So I have move forward 1 meter. You can see that on line 11 in green with the two slashes for comments. And then we're going to turn both motors on at norm P. So how do I do that? Well, if you remember earlier, we said the motor control command is going to be motors. Then we have a square bracket because we're talking to the control, to Cortex. It's going to say right motor, square bracket is equal to norm P, semicolon. Remember, this is going to be a simple command and it's going to need a semicolon. So I turn the right motor on. Then the next thing I want to do is I want to go forward and straight. So I need to do the same exact thing for the left motor. So I have motor, square bracket, left motor, and then close square bracket equals norm P and a semicolon. So that's the two things. So now one of the things that happens with motors is they're just going to run until we tell them to stop. So what we're going to do is we're going to do a pause, and we're going to say we're going to keep this condition going, which is both motors running at norm P, for 1850 milliseconds. So how do we do that? Remember, it's wait 1 msec, and it's 1850 in parentheses. Now the M is capitalized, so that means milli, and it's milliseconds. And then again, that's 1850 milliseconds. So what does that equal? That's going to be equal to 18 or 1.85 seconds. And we would actually have written our very first program. Not bad. We have 14 lines, 16 lines of code if you count the curly bracket at the end. Not too bad. Now I do actually want you to run here. So what you would do now is you would go to compile. It's up right under the word C. It's let's code. It's compile. And we would do that. And if you did it exactly like you should, you would have no errors. And then you would then go to download to robot. Now, obviously, you have to have your robot set up. So all the wires need to be set up. All the VexNet communication needs to be set up. So we have all of that happening. You download to robot, and then you would actually hit start once you download to robot. And what that's going to do, it's going to send your robot at right motor at norm P, left motor at norm P or 63, and it's going to do that for 1850 milliseconds. Now, here's something that's kind of weird. When we do all these calculations, we always make it so that every condition is perfect. Every rotation of the wheel goes exactly the same amount. There's no slipping between the wheel and the ground. The motors are all running perfectly. They're all getting the same power. The temperature's right. The battery power is full power. Everything is perfect. And unfortunately, That's not what actually happens. So we have a difference between calculated values and actual values. So we're going to run this program and we're going to see what does it take, how many milliseconds does it actually take to get to 1 meter. So you're going to run this, and if it goes over, that means that 1850 is too big and you're going to cut it down some. If it goes under, that means 1850 is too small and you need to increase the weight 1 MSEC. So I want you to continue to do that. We will be doing that for almost every challenge, so that every challenge is going to have something where we have to do some actual calculations, actually measurements, to verify our calculations. So calculations are nice, but they don't take into any of the other stuff that we need to take care of, like friction and all that stuff that's just not there. It's always a perfect condition when we use calculations. So we're going to come in and we're going to look at this, and we would end up changing our weight 1 MSEC to actually go 1 meter. Now, we're going to do the exact same thing for 2 meters. So that's actually our task 1 is done. We're going to do the exact same thing for 2 meters. Now, if I do 2 meters, if we go back to our calculations, and I'm doing the calculations for you, it actually means that we have 2 pause times. So instead of 1850, we're going to put in 3700 MSECs. Then for 3 meters, we're going to do 3 times that, or 5550 MSECs. And then the last one is going to be 4 times, and that is 7400. So that's going to be our start point, but that's going to be our calculated values. We're actually going to have to change that depending on what our actual values are. So we have to actually, when we get to our report, we'll see that we actually have to put our actual values in there. All right, so that's where we are right now. So let's look at what we can do next. So I just moved the screen up a little bit. And so there's my move forward. Now you might notice that I changed my weight 1 MSEC to 1755 because I did my test and I realized that 1755 is what it took. That's how many milliseconds it took to go 1 meter. So I'm going to use that for my next one too. So now that we've gone forward, I have to go backward. Now, how do you think I need to go backward? So we're going to put our comment in there. Well, I could do a couple things. I could take time backwards, which we can't do. It would be cool if we could take time backward. Or, which makes more sense, I'm just going to take my norm P and make it negative. So when I want to go backwards with the motor, I actually take motor, right motor, in square brackets, equals a negative norm P. So the negative is actually going to tell us that we're turning the motor backward. So if clockwise is forward, counterclockwise is going to be negative. Now again, I need to do both motors negative so that they actually will both go backward. And we're going to do our pause time again, and we're going to use weight 1 MSEC, and I'm going to do my best guess to figure that, well, if it took 1.755 seconds to get there, to get 1 meter, I'm going to guess that it's going to take 1.55 seconds to go back 1 meter. May or may not be the case. It would be pretty close. So we're just going to take our weight 1 MSEC to 1755. Again, I just matched the forward to the backward. All right, so now we are actually completed 2 of our 8 tasks. So we're right on track here. Now, I'm not going to do the whole program for you, so you're going to have to figure out how to go 3 meters, or actually 2 meters, 3 meters, and 4 meters. So go forward and backward to do that. So I'm going to let you work on that. So here's our main code again. And I want you to notice a couple things. Now, first of all, there's something called white space. And you'll notice that this code so far looks really nice and clean. Okay, so let's look at this. So the first term is white space. Now, white space is going to be all the space out in this program that we can actually see. And it's nice and clean. There's nothing extra in there. It's in order. Everything's in good place. So that's called white space. And white space is actually really helpful for the human to actually interface with a program. Now, I have had students put all of their code. Now, technically, you could put all of this code in one line, and it would just be one long line of gibberish. You wouldn't be able to understand it. And I actually just learned a new term, and it's called minify. Now, some programs actually do that for you. They take out all of the extra white space just to conserve on space, and it's called minify. Now, I don't like minify because we can't understand it. And I personally like to understand my code. So one of the things that we want to do is make sure we have white space. You'll notice that I have space on line 6 and 7. I have space on line 3, just to give me extra space. Again, I could cram all this stuff into one line of code and it would be super difficult to read. But remember, the idea of a program is we have to be able to, it's a human machine interface. HMI is what it's called. And we have to be able to read it. So we want to make sure that we have white space. Now, the other thing that I like to do, and this is really helpful, is to put comments in. Now, we talked about how to make comments before. Now, these are all single line comments, but so far in 16 or 18 or 20 lines of code, I have 4 comments in here. Actually, 5 comments if you count the pragma statement. So I have a comment that's saying, hey, here are my variables. And then we say norm P, we identified it and then said, this isn't my normal power. And then line 11 says, this next set of code, what I'm doing here is I'm actually going to move forward 1 meter. So then I say what I'm going to do, and then I do it. And then line 16 is I'm going to move backward 1 meter. So then I do that. So this is, again, just telling you how the program is running. And it's, again, I'm going to be looking at this from a programming standpoint, but if another teacher would happen to look at this, they would be able to look at this and say, this is what this person's doing. They're on line 11, they're going to move forward 1 meter. Then they're going to move backward 1 meter on line 16. So they'll be actually able to interpret what's going on. And again, one other thing to remember is the comments are not read by the program. So they're just skipped right over. So they don't take any extra time on computer time. So we don't have to worry about it. It's like, that takes too much time to read. One other thing that I would caution against is let's not comment every line. Once we get something down, we could just say, hey, this is going to be moving 1 meter. I don't have to say we're moving the right motor at norm P, and then we're going to move the left motor at norm P, and my weight 1 MSEC is 18 or 1755. Okay, I don't have to do that. It's not good practice to comment every line, just the group of lines so that someone else could understand it. And it's also easier for you to understand where you are as well. Okay, so those are 2 things. Now let's go to our report, since this is the very first report you'll see. Okay, so let's go through the setup of it. So first of all, you have a point value. So this first report is going to be worth 24 points. Okay, so the next section is my objective. What are we actually supposed to be doing in this challenge? A lot of times, if you go to the objective, you can actually start working out some of the pseudocode. So in this case, I'm telling you the pseudocode. Go forward to the first 1 meter mark and then reverse to the start box. So that's actually the first 2 steps, the first 2 tasks. And then I tell you what the next 2 tasks are. So the objective is going to be giving you a hint of what my pseudocode or what your pseudocode should look like. And then the next set is I tell you the skills you're going to use. So we've learned about how do I set a motor command? What is a weight 1 MSEC command? And how do we do comments? So I've told you how to do that. And then each week or each challenge, we add more stuff to that. So by the end of this, we'll be doing some pretty cool stuff, and you'll be amazed at what we can get your robot to do. So the next thing we're going to do is we're going to update our global variables. Now, in this case, we don't have any yet, so we're just going to put our very first one in. Now, this is going to be worth 2 points. So as you can see here, I'm telling you is the type is an integer. Okay, I left the next couple lines blank, so the next one's going to be the name, whatever you want to call it. So I would recommend norm P, but if you like something else, I have students that don't like norm P and they pick something else, and then you give it a value. And then you put your comments on it. So that's going to be our global variable. This is worth 2 points this time, and then every time, every other challenge will have this section in there, and we'll be adding more each time. So let's look at report 2. So here's actually the course. So I have a little drawing of the course for us. Okay, then we have the pseudocode. Remember, this is the plan that you're going to follow. It's worth 5 points. and it's written in this section. So I have 6 lines here. I usually put the number of lines that I think you're going to need. So there's 6 lines on this page. There's actually 2 on the next page. But this is going to be your tasks. How am I going to get this done? So the first line is going to say, move forward 1 meter. Line 2 is going to say, move backward 1 meter. 3 is going to say, move forward 2 meters, and etc. So that's how this is going to actually work. So that was page 2. Page 3, there's line 7 and 8. Then the next part of this is going to be your code. So your code in this case is going to be worth 8 points. And here's the rubric. And you can see that each of the different things are worth 2 points. So when you put a pragma statement in, you'll get 2 points. When you use your motor commands, you'll get 2 points. Use your weight 1 MSEC commands, you'll get 2 points. And use comments. Now, I have to admit, most of my students will lose points when they forget to put comments in. If they do skip that, they can lose 2 points on their command. Now, the other thing that I do here is I leave you a space over here to actually put a check mark or an X to say, yes, I did put my pragma statement. Yes, I did use my motor command. So you don't have to put the check marks in here, but I think this is a good thing to do. Did I actually use comments? Oh, I forgot. Oh, let me put the check. Let me do that. So this is a little check spot so that you can actually check to make sure that you've done that. And then lastly, you want to copy your code from Robot C, and you're going to paste it into this box. So make sure you include your pragma statement, your global variables, and anything you have in task main. So all of that is going to go inside this box, and you'll just cut and paste it. Don't worry about the formatting of it. Sometimes it doesn't look even. That's okay. Just cut or copy and paste it and put it into this box, and we'll all be good. All right, the next section, which is right now showing up on page 3, but it'll probably be bumped to page 4, is the calculations. Now, we've gone through the calculations here. I did it in the video, but I also did it in words here on page 4. The big key here is this equation that time is equal to D divided by C omega. And, I have an asterisk there. Okay, so we converted omega to revolutions per second. All right, so these are the calculations. And actually here we have the calculation. So we do the calculation. So you're going to do 2 meters, instead of D being 1 meter, you're going to put in for 2. And basically, I'll give you a hint here. You're just going to double the 1 meter value, and then triple the 1 meter value, and then quadruple the 1 meter value. So you can kind of cheat on the calculations there. But then lastly, we want to actually not lastly, but we have to get the actual time that it's going to take it. So this is where we're going to program 1 meter. We're going to actually change our time until we get it to actually go 1 meter. And then we're going to do a 2 meter, and then do a 3 meter, and then do a 4 meter. And we'll see how close they come to our calculated value. I rarely get anybody get it exactly on the calculated value. So remember, calculated value doesn't take into consideration different things. So we're almost there. The next thing is the completed challenge. And what this looks like, it means that you're going to say, hey, Mr. Aft, here I'm going to run my challenge. I want you to see it. So you put your robot in the box. You're going to hit start. It's going to go 1 meter, come back, go 2 meters, come back, go 3 meters, come back, go 4 meters, come back. And then I'm going to say good. And you're going to say, all right, very good. And we're all good. And then one of the things we have to do is we have to get a sign off. So what you're going to do is you're going to bring your computer over to me so that I can actually put a code in this sign off space. If you don't have the code in the sign off space when I go to grade it, you're not going to get these 4 points, because I am not going to remember that I saw your challenge. I have 17 students right now. I'm not going to remember whether someone did the challenge or not. So you must get me to sign off on this, or you will not get these points, these last 4 points, because this is your proof that you actually did the challenge. So you make sure that I see it, and I put the sign off in there. Okay, and then once you do that, then you can finally submit it to Google Classroom. All right, some last thoughts. Good luck with your first challenge. Remember, your classroom time is for running your robot and troubleshooting. All of your coding needs to be done at home. I know this is challenging. So make sure that when you do your troubleshooting, when you get to school, you can actually get your robots ready, download, run your robot, see if it does what you want. You can even compile at home, but you can't download to your robot. But if you compile at home and you see that it has a bunch of errors, here's the best thing to do. So if you have questions when you're at home, the best thing to do is copy your code into a Google Doc, a blank Google Doc, and then you can share it with me. That way I can look at your code and I can actually put comments in just like I would comment any other Google Doc. And that way you can see where your errors are. And then I can help you out that way. That's if you want to do this at home. So that's the plan. Hope everybody gets this, and good luck on your first challenge.